Okay, so I want to say something a little more systematic about second derivatives, which we mentioned in passing. Um, just to recall, we get a second derivative if we take the derivative of the derivative. Okay, so we have dy dx, which is a function of x, agrees to that idea by now, so we can take its derivative. We get the second derivative, which we can write two ways, d squared y dx squared, or f double prime of x. You might notice the kind of funky positioning of the exponents here when we write the second derivative that way. And the idea behind having the, like you're squaring the d and the dx, we're saying here is take the derivative of y 2 times with respect to x both times. Just so we're not being mysterious about this whole with respect to x business, some of our last units in Math Camp will be about multivariate calculus, where you have functions that depend on more than one variable. Multivariate, that's what that means. And a lot of the concepts that we're using here, that we're developing here, are just going to apply in a pretty straightforward way. But in those kind of situations, you do have to be clear about, well, am I taking the derivative with respect to x or y or whichever? All right, that's back to a world where it's just x. We're still writing them in the way that, that's clear. So back to the meaning of the second derivative. So the sign of the second derivative tells us whether the slope, that first derivative, is increasing or decreasing in x, right? So the second derivative often tells us, like, why are we even using a nonlinear function here? What's wrong with a linear function? A linear function has a second derivative of 0, right? Let's think about that. Linear function has a constant slope. The derivative of a constant is 0, so the second derivative is 0. So if we don't like the simplicity of linear functions, the reason why we don't like it is probably going to be represented by the sign of the second derivative. Okay, so let's just look at what different combinations of first and second derivatives look like. Okay, so let's first think about a function that has a positive first derivative and a negative second derivative. Okay, and that kind of function looks sort of like this. So you can see that, yes, we've got a positive slope here. The function is increasing, but if we kind of imagine those tangent lines here, they're getting flatter and flatter and flatter as x increases. Okay, so this is the kind of function that we might say is increasing at a decreasing rate. We might associate it with diminishing marginal returns. Okay, so functions that are increasing but have a negative second derivative, these get used to represent lots of kinds of benefits or utility functions. We might think there's diminishing marginal productivity. The first hour that I spend working on something is maybe less productive than the 10th hour because I'm getting tired and well, let's not go into the many reasons why I'm not as productive at the end of the day as I am at the beginning of the day. Or that the second piece of pizza doesn't taste as good as the first one does because you're not quite as hungry. It's not quite as wonderful. I'm not saying that this is always how things are. I'm saying that when you think that your productivity starts to diminish after you've been at it for a while, when you think that's true, that's like a thought that's not coming from math, it's coming from what you know about yourself or the world. The second derivative is what allows you to express that mathematically. Okay. So let's have another function here, still an increasing function, but now one that is increasing at an increasing rate. So it's got a positive second derivative too. So this function is like accelerating. So again, we're seeing those positive slopes. They're kind of flat here, just drawing the tangent lines. They're getting steeper and steeper. Okay, so we could call this increasing marginal returns. And these kinds of functions, we think those occur in the real world too. Any kind of acquired taste might have increasing marginal returns. You know, the first time you listen to some kind of experimental music, you're not really getting very much enjoyment out of it, but as you listen to more and more of it, you start to relate to it and start to actually enjoy it. Some less benign examples, increasing marginal returns. You have one drink, it tastes good. You have a second drink. Question is, does it taste better or worse than the first? And it's actually not so good if your enjoyment of drinks increases as you have more and more of them. Like so, increasing marginal returns are associated with behavior that might seem like addiction. Those kinds of objective functions produce destabilizing behavior. So beware of increasing marginal returns in some cases. You can also think of increasing marginal returns in production examples as well. So the first hour that you spend working on a problem, this is, I'm going to make exactly the opposite assumption of what I made over here. Sometimes the first hour you spend isn't all that productive because you're still figuring things out that you have to get to a certain threshold before you can actually make some progress. Okay, so again, the difference between the story I'm telling about being productive at the beginning of the day versus the end, two equally plausible stories, and we might think that one is true in some cases and one is true as the other. All I'm saying here is that we represent them with different assumptions about the second derivative. Okay, and just sort of filling out the set of pictures here with some negative first derivatives. So the case where we have negative first derivative and a negative second derivative, that's going to be function like this, and negative first derivative and a positive second derivative is like that. Okay, so here with the negative first derivative, the second derivative is also negative, is the slopes are getting more and more negative. It's always a little bit harder to go back and forth between the words with the negative relationships because the slope is decreasing, but it's becoming a negative number that's greater in magnitude here. So it is actually becoming steeper in this case. And here we've got, again, a negative slope that's sort of flattening out, becoming closer and closer to 0. So it's increasing on the number line, right? A slope of -3. If we go up to a slope of 1 here, the slope is decreasing. It's from -3 to -1 to -1/2. The negative numbers are getting closer to 0, even though they're increasing in magnitude. Just flagging that annoying situation where our ordinary language way of talking about what's happening kind of clashes with the mathematical relationship between two negative numbers. Okay, what else do I want to say here? Maybe I can say this, just keeping on this page. These functions over here in this column here, the functions where the second derivative is less than 0. Okay. The second derivative is less than 0. We would say is that f of x is concave. Okay. And over here, where the second derivative is, oh, sorry, I think I said that right, but I wrote it wrong. So look at what I'm doing here. Let's go back, do it correctly. The second derivative on this side of the board is negative, And I did, in fact, write the right word here. A negative second derivative, it goes with a concave function. Just defining the term concave, that's what it means mathematically. And the positive second derivative is a convex function. And rather than continuing to cram stuff onto this page, let me go to a new page here. So sometimes we have functions that have the same sign to their second derivative no matter what. So second derivative less than 0 for all x, we would say that is globally concave. Second derivative positive, all x, that is globally convex. So something like x to the 4th power, we take its derivative twice. First derivative is 4x cubed, take the derivative of that, we get 12x squared. Because we've got this square term here, that is indeed always going to be positive no matter what x is, so that is indeed greater than 0 for all x. So that function is globally concave here. We took the negative of the function, the second derivative of negative x to the 4th power would be negative 12x squared. It would be negative for all x, so it would be globally concave. Lots of functions aren't globally concave or convex. Some of them change their concavity. So for example, the second derivative of x cubed. So the first derivative is 3x squared, second derivative is 6x. That is less than 0 for x less than 0 and greater than 0 for x greater than 0. So x cubed is a function that changes its concavity. It changes from increasing at a decreasing rate to increasing at an increasing rate. And it looks like this. So here it's increasing, okay, but getting flatter and flatter as we get closer to 0. Still increasing here, but now increasing at an increasing rate. So the first derivative is positive for all x. So it's globally increasing, but its concavity changes. Okay, so as I said, second derivatives have a lot of substantive meaning. They are usually the answer to the questions why the function isn't linear. Is it a function that has a slope that's increasing or decreasing as x changes? Second derivatives, for that very reason, are really important in optimization problems, which is going to be the thing that we'll look at in the next unit. So I'll see you then.